So let me draw a MOSFET for you. So what I'm drawing is a N-channel enhancement mode MOSFET. Right? N-channel enhancement mode. So I'm going to draw that, and let's see if I draw it correctly. All right, so I've drawn a MOSFET. Okay, so is that a correct MOSFET, or there are problems with it? Huh? So which is the most, the glaring error which is staring in your face? Body? All right. So does everybody agree that this should be P? All right, so we'll correct. Okay, so it's P. What else? Anything else that you see wrong? The one in red is where I've drawn the oxide. It's a MOSFET, right? MOSFET. So MOSFET, MOSFET. So there's a metal, there's an oxide, there's a semiconductor, right? So in red is the oxide. This is oxide. And this is the metal, right? And this is my semiconductor. Which is for us is silicon, right? Anything else besides the fact that you said that the body, this is what we also call the body, right? The body of the MOSFET. So you're saying it should be P-type. All right, accepted. Anything else? Huh? N region should be under the metal. So what he's saying is there's something wrong with this edge. There's something wrong with this edge here, he's saying. That edge should be under the metal. So there are, the hint is there are several problems, okay? So you've identified one. He's saying that the edge of the source should be under the metal. So where should I shift it? Should I shift it here? Let's put it here. Should it be here? Will it be okay then? So let's erase this. Is that better? Under the blue one, okay? So what you are saying is, so is that better? Is that better? Why are we doing that? Why should it overlap with the metal? Why should it overlap with the metal? Why not do this? What is wrong with this approach? Why aren't we just leaving it here? What will this do? What if somebody were to make a MOSFET like that? Huh? So what he's saying is, note that the MOSFET, the important word in a MOSFET is also field effect transistor. Field effect transistor basically means that the MOSFET works on the basis of the concept of a parallel plate capacitor. That if you apply let's say a positive charge here, then a negative charge forms on this particular plate here. So, and the negative charge is the channel. So under the present circumstance, the metal is here, so the channel of electrons will form only here. And there is no channel here, and there is no channel here. So source and drain, the whole idea is that the source and drain should get connected by the channel. So if you put metal only over that part, you are going to create, according to the parallel plate capacitor, you're going to create a channel only under the gate here. You will not create in that outside region. And since you don't have channel in the outside region, the transistor will not work properly. Right? So what we can do is we can correct it in several ways. One way in which we can correct is extend the gate all the way here, put gate all over, let's say, and as rightly said, extend the source under here, extend it here and extend it here. So note that the other change that I made was, it's not vertical. This is not, you don't, when you introduce a dopant into a semiconductor, it just doesn't go in a straight line. And you don't get edges which are sharp. So you get these curves here. You get a curve here. You get a curve here. Right? So these boundaries are curved. And now, at least, the channel would be all over the place. So the error was that the gate and the N plus, the third error that none of you are talking about, this is not N, this is N plus. Why? What is the difference between N and N plus? N and N plus? N and N plus. N, basically, when we write N, we mean doping of the order of 10 to the power 16, 17, and so on and so forth, right? Now, when you form a channel, the concentration in the channel is very high, and you don't want voltage to be dropped in the source and the drain. So that's why you make them heavily doped. These layers are heavily doped N plus. That's why we call it N plus, in contrast to a normal doping, which we call it as N or a P. All right? So that's the other one. So it's N plus. The gate and the source and the drain should overlap so that the channel connects the source and the drain. Any other problem? Any other problem with the design? Or with the diagram? The diagram gives you the impression. What impression do you get about this by looking at the diagram? What is this and what is this here? This is the total thickness, right? Where are you making the transistor? You're making it on a wafer, silicon wafer. And so this is the thickness of the silicon wafer. And this is what we call as the junction depth. You know, you have diffused N plus region and formed a junction, right? There is a PN junction, as you can see here. There's a PN junction here. So the diagram is it gives a false impression as if the junction depth that you see here, this junction depth, this one, is a significant fraction of the wafer thickness. Now, the trouble is that the silicon wafer thickness is around, say, 400 micron. 400 micron thick. The junction depth is less than 0.1 micron. The junction depth is less than 0.1 micron. All right, so it gives an impression as if the MOSFET that I've made, it forms a significant fraction of my wafer. The MOSFET just exists in the top. You can calculate how much top, very small percentage of the wafer here, right? So wafer is 400 micron thick, and the MOSFET is just at the top surface. The rest of the silicon wafer plays no role, except for providing a mechanical strength and stiffness to the wafer. You don't need a 400 micron thick as far as the MOSFET is concerned, but you have to make 400 micron thick because so that you can hold it and you can do processing over it here. Now, we cannot draw something which is 400 micron or whatever. If we were to draw this diagram on scale, then the diagram would look very funny. You won't be able to see the N plus and the channel and things like that. You won't be able to see. And so for that reason, please take it as that this is not drawn to scale. The diagram is not drawn to scale, okay? All right, so that's, keep that in mind, that this is 400 micron and this would be less than 0.1 micron. So that's the other one. Okay, so let me, as I said, write a few more things about the MOSFET here. Okay? Any problem? That would be? You mean I cannot plot IDS versus VGS? I can plot, right? Okay, so what he's saying is that this should be, in the way the diagram has been drawn, this should be what? VDS. And this should be? VGS. All right, VGS, fine. Okay, we draw like this. This should be? Is it okay? So now you're thinking that everything I'm writing is just the opposite. So which one is the saturation region? Which one is the... So why this is being said is, remember which one was the saturation region in bipolar? Bipolar was where I've written, and in a MOS, the saturation region is not this one, so this is wrong. This is wrong here. So what we need to write is, this is sat, and what do we call this? Does it look linear? You're saying linear. Does it look linear? Why are we calling it linear? Another name for it? Another name for this region? Huh? Triode. Why are we calling it triode? Where is this triode coming from? So it is called linear. The reason why it's called linear is that if you examine the region very close to VDS equal to 0, close to the origin, you find the characteristics are linear. Characteristics are initially linear But of course, as you approach, they start bending here. They start bending here. So it's not, the whole region is not linear. The ones close to the origin is linear. And the reason why we call it as a triode, what I would suggest is go and read the first paper that was published on transistor. The first paper that was published on transistor, the title, if I remember correctly, was Transistor, a something like this, a semiconducting triode. Something of this sort. Transistor, a semiconducting triode. If you do a Google search, you can come up with this particular paper. The first paper on transistor, published on transistor. This was in 1948. And who were the authors of the paper? First paper on transistor. These are the foundation of your discipline, right? Transistor. Who were the authors? You should know that. Who were the guys who invented the transistor? Huh? Shockley. He's saying Shockley. Should he be an author here? Author of this paper? The authors of the paper were, yes, Bardeen and Brattin. The first paper published on transistor did not have the author as Shockley. The first transistor which was invented by these two guys here. The eventual Nobel Prize that was given because of Shockley's other works was given to both. Shockley also was a recipient of the Nobel Prize that was given because of his other works on, related to transistor here. But the first paper, so it would be nice if you just go and do a Google, look at the first paper that was published on transistor, and note that before 1948, how was electronics done? Electronics existed before 1948, right? How was it done? Using vacuum tubes. Using vacuum tubes, and an example of vacuum tube is triode. So when they had invented something new, and how do you describe something new to the people that have invented something new? So you say, well, it's like a triode, but not using glass and vacuum, but it's a semiconducting triode. Right? So some of the things that you see here, triode and all that, they are coming up. The reason why we are calling it triode, because of the relationship to of the characteristics to the triode which the transistor replaced. All right. So in saturation region, I'm going to write down the current. Any problem with this equation? What is the problem? W by L. Why not L by W? Why do you think? Yeah, you remember from your memory it should be W by L. What's wrong with L by W? It is wrong, but why is it? Why do you think immediately by looking at it, it should not be L by W? It should be W by L. Aside from thinking from your memory. Huh? If you increase the channel length, the current decrease, right? The carriers will take more time to, yeah, that's true. So this should be, what you are saying is L, all right, so that your intuition is right. It should be inversely proportional to L. As I make the channel longer, basically the source and drain are separated by a longer distance. The resistance increases between the two, the current goes down. Anything else? Anything else that you think is wrong? It's saying this should be minus VGS minus VTHN. Any other problem with this? Is there a problem with COX? All right, so COX, what he's saying is COX should be, remember, if you recall what is COX, so COX is equal to E oxide by T oxide. E oxide by T oxide. So when I write at the bottom, it says IDS is proportional to T oxide. While if I write at the top, IDS will be inversely proportional. So the issue is, should IDS be proportional to T oxide or should it be 1 over T oxide? Again, what I would like you to remember is that MOSFET is based on parallel plate capacitor. The principle of a parallel plate capacitor. So if you bring the plates of the two capacitors closer together, what would happen? You would create, for the same voltage, you will create more charge. You'll create more charge, and therefore the current should go as 1 over T oxide. So besides, what I'm trying to tell you is, besides your memory that it should be 1 over C oxide or C oxide should be in the numerator, you should have an intuitive feel for how does this MOSFET work and why it should be in the numerator. All right? Okay. Let me draw another characteristics. Anything wrong with this? IDS versus VGS. Since I've been drawing lots of wrong things, so is there anything wrong in this also? Huh? Nothing wrong? What is the current here? Current here? This is threshold. Threshold is somewhere here, right? Below threshold, current is? Below threshold voltage is the current. What is the value of current? Is it equal to 0 or is it? Which is the correct picture? Below threshold. Is it below threshold you think the transistor is not conducting? If threshold voltage is, let's say 1 volt, right? I take a MOSFET. I take a MOSFET here and I apply 0.9 volt, right? I apply 0.9 volt and I put a resistor here or whatever. You think no current is flowing through the MOSFET? This graph is again very misleading. Is highly misleading when you go towards values below threshold voltage. It gives an impression that the current, as some of you are saying, that the current is 0. Well, the same graph, if I were to plot on a log axis, same VGS, but note that I'm plotting on a semi-log scale here. So this is log of IDS. Log of IDS, what you would see a graph like this. You would see a graph like that. And somewhere here is where you would see VTHN, threshold voltage. That's what you would see if you plot it on a log scale. So when you do that on a log scale, you then realize what is the nature of the MOSFET as you go below threshold voltage. The current is not 0. The current is not 0. What is happening is that the current is falling rapidly. If you see a straight line on a semi-log paper, it means that the characteristics are exponential here. So the current is exponentially falling here. The current is exponentially falling here. While above threshold, the current is Actually, we just saw VGS minus VTHN square. It goes as square. Above threshold, it goes as square. Below threshold, it falls exponentially. So the current is, do not confuse by looking at it in the linear graph and think that below threshold, the current is 0. The current is falling. Let's say the current here is 1 microamperes. The current here may be 0.1 microamperes. The current may fall to 10 nanoamperes, 1 nanoamperes, and the current is continuously falling, exponentially falling. All right? So the current is not 0 below VTHN. It is falling exponentially, and then depending on where you are, the current may be small according to whatever measure you have. Before we finish, one last thing here. All right, any problem with this? Huh? Body should be connected to? Okay, so what you're saying is do not connect the body to the drain. Do not connect it here, but connect it to the source. What if I connect it to the drain? Nobody is stopping me. I can connect it to the drain. What will happen? What will happen if I connect it to the drain? Huh? Body effect. What is body effect? So no, there's something more, something else will happen. Just think about, say I put 5 volt here. Think about if I put 5 volt here, and let's say there is a drop here of, let's say, 3 volt here. Drop of 3 volt. So the voltage at the drain is 2 volt. Right? The voltage at the drain is 2 volt. Draw the MOSFET, take the body, connect it to the drain, and then the body will also be at 2 volts, and see what would happen. What is going to happen in your MOSFET if you connect the body to the drain? Just check what will happen to the MOSFET there. Okay? So what we're going to do is, from the next lecture, we'll start a discussion related to MOSFETs.